So welcome to today's lesson on simplifying radical expressions. So today we want to try to understand how to simplify radical expressions, and hopefully that'll make a little bit more sense here in just a minute after I show you some radical expressions that can be simplified. But before we do that, we're going to go back to the basic idea that we're beginning with, in that we get these radical expressions oftentimes by finding side lengths of squares. And so this first square has an area of 2 if we figure out the little parts of it. And so that means its side length is the square root of 2. And so that's what a radical expression is. And it's an expression that's a root, a square root, or other cube roots and so on. But in this case, we're only going to be looking at square roots, which really come from the side lengths of squares. So that distance from here to here is actually the square root of 2, or from here to here. Any side of that square has a length of the square root of 2. So I could describe any side of this square with the square root of 2. So all the way around this square, any side length is the square root of 2, which we could calculate out to 1.414, but it's actually just as accurate, in fact, in many ways more accurate, just to describe that length as the square root of 2 from a corner to corner. It's really the diagonal distance across a square. And so if I go to my next square and I find the area of this square, which is 8, that means the side length of this square is the square root of 8. And that's one way to describe the side length. So all the way around, all the different sides of this are actually the square root of 8 long. But what we did in the first one was we actually found that the diagonal distance across a pair of squares, like from here to here, just this distance alone right there, is the square root of 2. And so is this one here. So we actually have a pair of square roots of 2. These two parts, these two spots together, are each the square root of 2. So what that actually means is that the square root of 8 can be simplified, or can be written another way, can be written. A lot of times we say simplified because that's what we kind of consider this as. We're getting the root to be the smallest possible root. So in this case, the square root of 8 is fairly large, but we can write it, or rewrite it, can be written as 2 square roots of 2. So 2 of these. So that distance, the square root of 8, is the same as 2 square roots of 2 long. So in this case, we call this, or we would consider this to be a simplified version of the square root of 8. And the reality is that these two things are equivalent expressions. In other words, they're equal. So equivalent expressions, they actually would equal the same thing. If we were to put 2 square roots of 2 in a calculator and the square root of 8, we would get the same number, about 2.8 is the square root of 8. So that would be that distance across there. So we have these equivalent expressions. Now another way to think of this is, if we didn't have the square, is that the reality is roots can be factored just like any other number. So the square root of 8 is actually equal to the square root of 4 times the square root of 2. 4 times 2 is 8, so this is really the square root of 4 times the square root of 2. And so another way to think of this is, in simplifying it, if I didn't have the square to look at, I could just think about factors of 8, any of which are perfect squares, which the square root of 4 is. I actually know the result of that is 2. And so here again I get my 2 square roots of 2 in another way. Both ways give me the simplified version of the square root of 8. So what we did was we took the square root of 8 and simplified it, or rewrote it, into the smallest possible root. So the square root of 2 is a lot smaller than the square root of 8, and so in this case we consider this to be a simplified version of that. So if we look at another square down here, this square actually has an area of 18. I'll go back later and Actually make sure that that's true, but I believe that the area is 18, so which means that the side length is the square root of 18. But if you also notice that the side length is actually 3 sections or 3 parts that are all equal to the square root of 2. So I have the square root of 2, the square root of 2, the square root of 2. I actually have the square root of 2 3 times. So this really is 3 square roots of 2. And once again, all I've done now is taken the square root of 18 and rewritten it, because I can say the square root of 18 can be written as 3 square roots of 2, or 3 times the square root of 2. So again, we have a simplified version of the square root of 18. Okay. So I could have taken the square root of 18 and thought about factors of 18, like 9 and 2. 9 times 2 is 18. So you can actually factor the square root of 18. One of its factors is a perfect square root, and the other one is the square root of 2, which is one we don't know. And this one, because I know the solution to the square root of 9 is 3, I can rewrite this 3 square roots of 2. So you can see we got the same answer by looking at the square and the side length parts of it, or just taking the square root of 18 and finding the factors of it that give us a perfect square root and then the smallest possible root that we don't know the answer to, or at least without a calculator or approximation. Square root of 2 is approximately 1.414, and so because we can't get an exact value for it, we just leave it as the square root of 2. But we can get an exact value for the square root of 9. So once again, we can say that the square root of 18 can be simplified to 3 square roots of 2. And again, they are equivalent expressions. Equivalent expressions. They are equal to each other, but we consider this to be the simplified way to write it, as the smallest possible square root number. So we have equivalent expressions now. So let's try this with a different square, a couple different squares. One more time, just so you can understand that the whole idea of simplifying is just using the smallest square root possible in any measurement. So in this measurement here from this square's edge, the area of the square is 5. So the side length would be the square root of 5. And that's really as simple as that one can get. But if I look at the next square over, this one actually has an area of 20, which means the side length here is the square root of 20. But if you notice that this distance is actually the same as this distance here. The square root of 5 distance here is the same as from here to here. So I have a square root of 5 there, and then the rest of it is another square root of 5. And so what you actually have in this case is 2 square roots of 5 equaling the square root of 20. So again, I have a simplified radical form. This is my simplified radical form. And I could have, if I had thought about the factors of 20, which are 4 and 5, so you can actually factor square roots. So the square root of 20 is the square root of 4 times the square root of 5. But I know what the square root of 4 is. That's equal to 2. I don't know what the square root of 5 is exactly, so I just leave that alone as the square root of 5. And so now what I have is the simplest radical form and what I have is equivalent expressions. So two ways to write the same thing. And so that's what we mean by simplifying radical expressions. We want to have the smallest possible radical in the answer. Square root of 20 is not the simplest radical. The square root of 20 can be simplified down to where it only has the square root of 5 in it, and then a whole number 2. So it means I have 2 of these. And really, literally, it comes from that there are 2 square roots of 5 that make up the square root of 20. So let's do a few more examples of this, but without the squares. So what if I just had a square root number? How do I figure out what to do with it? So let's say if I start with the square root of 32. And I say I want to get that in the simplest radical form. So here's what I want to do. I really want to look for factors that are perfect squares. So if I think about my perfect square numbers, like 2 squared is 4, and 3 squared is 9, and 4 squared is 16. And I could have right away said, well, 4 is a factor of 32, so that might work. These are perfect squares. But also 16 is a factor. Now let me do a couple more just so I have them. 5 squared is 25, and so on. So I should know all of my perfect square numbers: 4, 9, 16, 25, 36. These are called perfect squares, square numbers. So 4, 9, 16, 25, 36. If any of these numbers are factors of a number, like 16, that means I could factor, and I could go on and on with these numbers, but I could factor out the largest one from this. So the square root of 32, see, 32 is equal to 16 times 2. 16, that's the largest perfect square factor. And so what that does for me is that now I can take that square root of 32 and factor it into the square root of 16 times the square root of 2. And because I know what the square root of 16 is, it's 4, I can know that the square root of 32 is equal to 4 square roots of 2. Now I have it in the simplest radical form. And now they are actually equivalent expressions. And I could do this with any radical. If I had a radical, like, do one more here, get the idea. If I said the square root of 45, and I want that in simplest radical form. So I start thinking about my factors of 45. And I think of all the different ways I could factor 45. I could say 45 is 3 times 15, or it's 1 times 45, or 9 times 5. And so as soon as I see any pairs of factors that have a perfect square number, like 9 is one of our perfect square numbers in it, then I know I'm on target. If I look at the other number and it's not a perfect square number or doesn't have any perfect square numbers as factors, then this is the pair I want right here. So that means the square root of 45 would be the same as the square root of 9 times the square root of 5. And so now all I need to do is solve the part I can, which is the square root of 9. I know that is 3. And that would stay the square root of 5 because I don't know what that is, at least not directly. So now I have the square root of 45 in simplest radical form. So really, ideally, when you're trying to simplify things, you want to look for factors that are perfect square numbers and actually literally factor the number into those factors and then solve the part that is solvable, the perfect squares, square roots, and then you'll have them in simplest radical form. And what this does is this gives us actually a length. If I were to actually, if I knew that this distance from here to here is the square root of 5, which I do because I did it on the other side, I know that's the square root of 5, then that length is actually 3 of these. 1, 2, 3. That distance right there from there to there is actually 3 square roots of 5, or the square root of 45. So these really have a use in terms of describing distances between points on lines. They're not just simplified to simplify them. These are like measuring sticks. The square root of 5 is a distance between places on grid or on dots. And so now I know the square root of 45 is just from here to here because it's 3 sections of the square root of 5. And so that's what we use them for when we simplify them into those forms. It just gives us another way to look at it. It gives us the smallest possible radical in the actual expression as opposed to a much larger radical in this expression that actually has factors that could be simplified. And so that's kind of a quick overview of how you simplify radical expressions. So we summarize this by saying to simplify a radical, we want to find factors that are perfect squares, change it into those factors, and then solve the part we can and leave the other part. And then in the end we'll have the simplest radical form and a set of equivalent expressions. Gives us 2 ways to describe a distance on grid. Hope that helps.